We can use our understanding of how to solve a differential equation to actually derive the equation that models exponential growth. First off, what is exponential growth? It's when the rate of change of a population or some substance, etc., which I might just refer to as stuff, when the rate of change of some stuff is proportional to the current amount of stuff, we can model that growth or decay with an exponential model. So let's think about what we're saying here. We're saying that the rate of change, and I've just written this out previously, the rate of change of y is proportional to y itself, okay? And another way of stating that same thing is that the rate of change of y, right, the rate at which y is changing is proportional, or that is to say, it's equal to the constant of proportionality, times the amount of stuff y that you have at time t, okay? And if we wanted to assign variables to represent these, we would say that the constant of proportionality here, we can say is going to be some value k, and the amount of stuff that you have of y, we're going to describe as being our y value. And if you look carefully here, that's exactly what we're saying. So just to recap, the rate at which y is changing with respect to t is proportional to y itself. Or another way of saying that, it's the constant of proportionality, k, times the amount of stuff that you have. Now, if you look carefully at this equation here, what we've just stated, this is a differential equation. So let's solve this differential equation. And this is actually going to give us the law of exponential growth or decay. So let's do that. So the first thing we're going to do, and if you need to review my previous video on solving differential equations, we're going to solve by separating our variables. So we're going to say 1 over y dy is equal to k times dt. Next, we are going to integrate both sides. So the integral of 1 over y is the natural log of absolute value of y. The integral of some constant k with respect to t would be k times t plus some constant of integration. Now we're going to exponentiate both sides. We're going to write both of these as powers of e. This then gives me the natural log, or the e raised to the natural log of y is just the absolute value of y. And this again is going to be e raised to the kt power. And I'm actually going to call this previous constant here c sub 1. And I'm going to say this as the following. I'm going to say, let our big C be equal to plus or minus e raised to the c sub 1 power, okay? So that's going to allow us to take care of this absolute value. And so we're writing this times c, and then just move that constant to the front. And this is the law of exponential growth or decay. And this should be a formula that should be somewhat familiar to you if you're in this course. You should have seen it when you talked about exponential growth in your pre-calculus course. We can use this to model things like half-life, or even the famous continuously compounding interest problems. So these are all examples of things that we may have seen before. And I'll link some videos on this in the description below. So to recap, exponential growth occurs when the rate of change of a population is directly proportional to y itself. Solving this exponential differential equation gives us the law of exponential growth, where y is going to be equal to our constant, our initial value, times e raised to the kt power, where k is the constant of proportionality, and I'll just abbreviate as proportionality for short. Also important to know that when k is greater than 0, we have growth, and when k is negative, we have decay. T is equal to time, and then y is equal to the amount of substance that you have, or the amount of stuff. And remember that y is a function of t. Okay? All right. So with that said, that's really the main reason why this lesson appears in this particular unit, because we needed to be able to solve a differentiable equation, or differential equation, in order for us to understand where this law of exponential growth comes from. But let's just look at a couple quick problems, all right? So looking at these here below, what is the rate of growth of a population in a city whose population triples every 100 years? Let's assume that the growth can be modeled by the basic law of exponential growth. So we're going to say y is equal to c times e to the kt power. Okay, based on this, if the population is tripling every 100 years, we're saying that y, okay, the amount of stuff at a certain time, is going to be 3 times whatever your starting value is. Okay, your k is what we're effectively going to be solving for, and your time is 100. Now, we didn't actually really need to write these c's here, because if we divide both sides by c, you're going to get the following here. So you could actually just jump right into this step if you know that your initial population is going to be tripling after 100 years. Now from here, we actually need to solve for k, and we're going to do that by taking the natural log of both sides, right? So if we take the natural log of both sides, we would have natural log of 3 is equal to the natural log of e to the 100k power. And let's finish this off over here. So we've got the natural log of 3. Using the same exponent properties, we can say that this is equal to 100k. Okay. K then has to be equal to the natural log of 3 over 100, which is approximately, approximately 0.011 or 1.10%. Okay. So that is the growth rate of that population when the population is tripling every 100 years. Okay. All right, let's try another one. Let's find y, which will represent the mass in kilograms of a radioactive element whose half-life is 4,000 years. So those of you not familiar with half-life, what we're saying is that the amount that you have, it's referring to the amount of time that it will take for whatever your current amount is to reduce or decay down to half of its original amount. So if you have 200 pounds of an element, you're trying to figure out how much will there be after 1,000 years if you know its half-life. So let's use the same exponential growth equation. And let's fill in what we know. We know the half-life. We're saying that y will be half of its original amount, okay? Half of its original amount. When t is equal to half of its original amount, when t is equal to 4,000, we can then solve for k here. Just like we did before, we're going to take the natural log of both sides. So if I take the natural log of both sides here, we then say this is the natural log of 1/2 is equal to 4,000k. Oops, 4,000k, not 400. K then would be equal to the natural log of 1/2 all of this over 4,000, which is approximately equal to negative 0.002. So now we know the growth rate, okay, or our constant of proportionality. We can then say, plug that into our equation. Y is equal to the amount. We have 200 pounds, or 200 kilograms, I apologize. This should be kilograms, not pounds, because we're talking about mass, times e to the negative 0.002 power. And to be more precise, we should actually be putting this in. Okay, but in any sense, you should get y is equal to approximately 168.179 kilograms. Okay. All right. Now, this last problem here involves Newton's law of cooling, which effectively states that the rate at which the temperature of an object is cooling is directly proportional to the difference of the current temperature of the object and the ambient temperature. So that is to say, if you place a really hot pie in the refrigerator, it's going to cool much more quickly than it would if you were to place it in a sauna. And the rate at which that pie would cool is directly proportional to the difference in temperatures between the pie and wherever it is. So if you have a hot pocket and it's removed from the microwave at a core temperature of 398 degrees in a room that has a room temperature of 68 degrees, after 5 minutes, you take a bite, you burn your mouth because the hot pocket is still 242 degrees, which is incredibly hot, right? And if you've ever eaten a hot pocket, you know there are only 2 temperatures for a hot pocket. It's blazing hot or ice cold. What you're trying to figure out is how long will it take for the hot pocket to be to reduce down to an edible temperature at 155 degrees. So it'd be a good idea for us to have the equation, the altered form of the exponential growth using Newton's law of cooling, which is y equals c sub s plus c minus c sub s times e to the negative kt. So this is the Newton's law of cooling form of the law of exponential growth or decay, where c sub s refers to our surrounding temperature and c refers to the initial temperature of our object. Okay, so let's plug in what we know. We know that we are y is equal to 242 degrees at the point when the surrounding temperature or the room temperature is 68 degrees. I won't write the degree symbol here, with its initial temperature being 398. So let's find a difference in the room temperature. We're finding the difference in the room temperature and the object temperature times e to the negative k times 5 minutes, right? Because after 5 minutes, the temperature of the Hot Pocket went from 398 to 242. So what we're doing is we're solving for k again. So just through some algebraic steps, we would get 330 e to the negative 5k. So let's get that constant by itself. So we can take the natural log of both sides, which then gives me the natural log of 174 over 330 is equal to negative 5k. And then k is then equal to the natural log of 174 over 330, all of that divided by negative 5. So now that we have that, let's plug that back in. Let me move down here. Let's plug that back into what we know. So let me do this in a different color. We've got 155 is the temperature we're looking for. The surrounding temperature of the room is still 68. The difference in the temperature between the object and the room is still 330. And we are going to plug in what we know. This is negative of negative natural log, or let me write it this way. Natural log of 174 over 330. Basically what we solve for a k to be times t. And now we're going to take the natural log of both sides after we have done some simplifying, and you should get the following. Okay, and I believe that should actually be positive. Okay, and t should come out to approximately 10.415 minutes. All right, and there you have exponential growth.